Bear with us, folks, here. We've got some technical difficulties happening in the background, but you should be seeing our guest speaker on your screen. And with me today is someone who we featured in past sessions, and we want to welcome Rags Srinivasan, who is Seagate's Director of Marketing for Growth Verticals. My name is Joshua Walty, Seagate's Global Partner Lead, and I'll be your host for today's session. Well, before we kickstart everything here, we just want to remind everybody to preserve the sound quality. You're all on mute, but we do want to hear from you. So find your way to that chat box in the either upper or lower right-hand corner of your screen and send us messages throughout the presentation, and we'll make sure that we address those at the end of the session. We got a lot to cover, so we won't be answering a lot of questions throughout the session. And we just want to remind everybody that after today's session, you'll receive a follow-up email with directions on how to access the content, so on and so forth. But enough from me. We have a lot to dive into, so I want to make sure that we get to the main show. So hang on just a minute, and let's see if we can find our presentation.
Good morning, everyone. This is Rags Srinivasan. Thank you for the opportunity, and thank you for giving an hour of your time today to spend with us to talk about some of this somewhat of a geeky topics on artificial intelligence and machine learning and everything. I'm very excited. So I have planned a set of topics today, which I want to start off with a brief summary of where we left off last time. For some of you who joined us about a month or so back, we talked at length about the edge. So I want to set the stage a little bit, bring out this concept, because you're going to see that is important for talking a little bit more into what we did on the edge with this very specific smart manufacturing case study. And then, of course, I will dive deep into our use case, how Seagate applied all those cool technologies, the edge, AI, and machine learning to take our factories into the smart manufacturing era. And of course, we'll make sure we leave enough time for the Q&A. And in terms of the topic depth itself, I will try to avoid getting too deeper into the algorithmic as well as the architectural details, because we do have a white paper that is coming up that will cover a lot more of it. So let's try to keep the topics at the high level, but if questions come in later on, we can go there as well. All right? With that, let's get started. Well, let's do a quick recap of our last webinar, which we talked at length about the edge as well. So the definition is important here, right? Like the edge really, it bridges the gap between where the data is created and then ultimately where the data gets stored and processed over a much longer period there. And if you're asking, well, is edge something out there? Do we need to worry about it or not? Well, the answer is actually the edge is here. And you're going to see today we have built out an edge use case of doing analytics on the factory floor. You're going to see a lot of this technology trends from the IoT, the artificial intelligence, and 5G that gets a lot of buzz about. They're all creating this whole new market and driving the need for edge. The last time we talked about, well, what are some of the edge use cases? Where do you see edge more often? We highlighted about 110 or so use cases and then did a deep dive on 3 of them: the autonomous vehicles, agricultural drones, and smart manufacturing. And since our expertise is in these factories and running factories and smart manufacturing, we will be covering even deeper with the real-life use case on smart manufacturing. All right, again, a very quick thing. People have asked me several times on the edge, is this the edge? Or they'll point out a box and then ask me, is this the edge? So they actually want to give a very clear definition there. The edge is not about the box itself, or it's not a product. The edge is defined by the location. It's outside of a traditional cloud scale data center. So the edge in that sense is very different from what you see as those much bigger, large-scale centralized cloud installations there. So in the case of, say, where you can find some of the edge deployments, in the case of autonomous vehicles, A cell phone tower that a car drives by, that could be the location of the edge. In the case of agriculture, the barn on the farm, that could be shared location, that could be the edge where you place data storage and data processing. And our use case for today, smart manufacturing, the factory floor becomes the edge where we place both the data storage and processing, where we put the data at work, right where it is created there. So that's a very whirlwind recap of what we covered last time about the edge. The edge is here and where you can find the edge, and that it's about the location more than just a form factor or a particular product there. With that said, I want you to think about briefly for this thing. Like you probably have heard many from other people, the IoT, the word popping around, and if you do a Google search, you'll find millions of these hits on this. I want you to take 30 seconds to think about this question. Like, what's the most impactful IoT device you can think of there? I mean, of course, the sensors, the temperature monitors, and all those many other things that come to mind, even your Fitbit, if you're wearing one there. In our experience and in our whole thesis of looking at the edge and the edge use cases, we believe the camera lens is going to be the most impactful of IoT devices. And you're going to see why. If I were to answer this now, if I end this webinar now saying to you what it is, it's because the camera lens captures so much information, so much context. And once you capture the images, the use cases for it are phenomenal. You can get it to anywhere from just finding a fault all the way up to improving your productivity and other aspects as well. Hence, you will see that camera play a huge role in machine learning and the future of IoT. And that will be the focus. Camera-based and image-based analytics is going to be the focus of the rest of the talk here as well. All right, let's start with the cameras with something more commonplace. Okay, let's ignore for a second some of the video surveillance cameras, and let's stick with some of the fun ones there. So this picture, actually, this kind of robot with cameras is showing up in some of the retail stores. They walk the aisles, taking pictures. Mainly what they do is they help find cleanup on aisle 4 kind of thing. It finds out where there is a spill or something on a particular aisle and helps send out an attendant to take care of it there. However, hidden behind this, the use case that we all don't recognize is that captures a lot more information. It's about how many people are walking around the particular aisle, how much time does a single person spend in front of a particular product, and then taking time to decide whether to pick that sugary cereal for breakfast or not. So it can, once you capture those images, it's going to give them a lot more information that they can later on give it to their data scientists to put it to work. That will help them for better product placement, better design, and everything you can think of. The thing that I want to make is it's all possible because of the images it's capturing there. This is this whole concept of what we call when these simple robots just moving around, when they get the eyes, they become a lot more powerful. And of course, I kind of joke in here that they're coming for us, but I don't know whether they're coming for us or not. But definitely they do collect a lot more information of value that's of use to many use cases and many organizations as well. So this is, I use this as an example to show to you it's not just outside in a specific factories or not, but let's show into how some of this camera-based, image-based analytics is becoming a reality in factories across the U.S. and the world. Well, there are news stories, if you were to find it, where many of the chicken farms, as well as some of the meat packing farms, are deploying cameras in their factories, and they use these images not just as a security measure, but they are using AI and applying those AI and those images to help the robots slice the chickens better. So it's just a very cool use case, but I am vegetarian. I don't know what it means to carve a chicken, so I would take a lettuce farm example. Some of the agricultural use case as well, you can see like how much to water, what level of hydration is needed, and what's the optimal way to keep those farms irrigated to minimize the cost. Again, the cameras are being deployed, and the images captured from the cameras are used to find out that right irrigation patterns in those lettuce farms. And you go all the way from food manufacturing to precision manufacturing, like the high-tech industries, like our own thing. You'll see high deployment of high-definition cameras to even electron microscopes that operate at the nanometer level in there. So it's not anymore the cameras is something out there in the future. We are seeing use cases emerging from even a chicken farm, a lettuce farm, all the way up to high precision manufacturing. And you can see that we will be going deeper into the third use case in here with the high precision manufacturing. All right, so when you think of factories, when you see many of the case studies done in the internet, as well as some of the ads you see of IoT and industrial IoT and things, first thing to notice is, well, our factories across the world are already automated to a large extent. You see from how the cars are made to how some of your semiconductors or even hard drives are made, there's robotics everywhere. That's not a new thing there. Those processes being getting automated for production there. But what is happening now is more and more the processes are getting very complex. And the things that we manufacture, the widgets I call them here, are getting a lot more sophisticated. And this is the world, especially in the world of hard drives or semiconductors or whatever it is, the manufacturing there is where a nanometer matters there. So you really have to work within very small window of tolerances. And the asks put on the system and on the people working there are become significantly high there. So that has a change from the past era of manufacturing to a lot. So the one common scenario that is in place in many factories with respect to IoT-based data is collecting sensor-based data. Like everyone today can quote you immediately, I want to find out if a particular machinery is going to break down or not, instead of having to stop the production line and then have a maintenance person come in and look at it, whether or not it's going to break down or not. Or worst case, let it run until it breaks, and then everything comes to a stop, let me then try to fix it there. So the IoT sensors that are put in place help get the overall health of these machines and help keep them running. What is now the new emerging use case is not just keeping up those machinery, but applying it across the entire production chain, all the way from where you get the materials down to finished products. They cross the entire the value chain where it can be used. Of course, it is done with real time, where when your production line is moving along, you want to be able to help improve the overall quality of the products you produce, the overall efficiency of the production process, all without bringing anything to the stop, and using more of data on what are the advanced technologies that are available. So that's this emerging high volume scenario that is of interest, and that's one is going to drive a lot more of data creation as well as data consumption, if you will. So just a note on Q&A. I know Joshua has muted everyone's line in there, and I'm not seeing the questions come through the chat, but please, I do see one or two, but please keep them coming. We have allocated good enough time in the end, so we'll dive into those questions as we come to that. So don't drop your questions yet. I'm just going to keep going on this one. So what is the new age of smart manufacturing, and what are some of the instrumentation, and what is going to be the preferred method of putting data to work here? Well, let's establish and recap here the needs of this smart manufacturing. Now, the use cases where we mostly go into. First, we're dealing with low tolerances. There is really no tolerance for error when you're operating at the nanometer level there. And then you are usually seeing a very high-speed production, like things move fast. Operators are asked to make about 20 to 30 decisions per minute. This has become a very high cognitive load on an operator standing there to asking them to make a good or bad decisions 20 to 30 times per minute. You can see that how difficult it is. Number three, well, the speed is not just with one aspect. The overall throughput, how much of units that get produced is also very high. You will see some example of how many units that we produce when we come into our Seagate case study as well. So the chosen method of instrumentation, if we want to help improve this big, large volume, high-speed process, is instrumenting them with either high-definition cameras or electron microscopes, and use that data then to help find out the bottlenecks and help improve the overall process. So, okay, we got the cameras and the instrumentation going. What comes next, right? Well, we get the images that are captured by these devices, be it the cameras or the electron microscope. Now you combine them with the deep learning models. I'll give you a simpler explanation of deep learning models in a second or so. This is more in the context of artificial intelligence and the newfangled methods of data analysis that are coming forth there. Together with the combination of all these images, plus these deep learning models, we now have a very effective anomaly detection tool in many of these high precision, high volume processes. In fact, once you solve for this very difficult, complex scenario, it is actually that kind of architecture and solution you can take it and apply it to other places as well. This is like when you are solving a problem at the nanometer level at this such high volume, you really are coming up with a very robust architecture that has multiple purposes outside as well. So today we will show you that particular architecture in this case. So briefly, how this would work in general. This is like more of a general case in here. First thing you would do is while your widgets are being produced, pass through the production line or assembly line, as the case may be, you will capture many, many images. In our own cases, we capture about 17 million images or so per day there. So we'll capture a very high rate of images. And then you'll send those images locally to both the storage and processing that is located within the campus. Now, most likely on the same factory floor, if not within the same factory campus there, where the training models that take in these images and help make the quality control actions based on the images received. So these things all happen at the millisecond latency level, so they can make very fast decisions and very easily make those 20, 30 decisions per minute that I told you about in there. So that's really it's come down to helping images, using images and helping algorithms learn better and help make the quality control decisions there. So that's more like the high generic level. Let's make that real and get into our own manufacturing case study where we put all these concepts to work with an internal project that we fondly codenamed as Project Athena. It's more of applying all those benefits of image analytics, deep learning, GPUs to help solve our own factory manufacturing quality issues as well as the throughput issues to significantly improve every one of those aspects and take it to the next level. So let me tell you which unit this concerns about, which particular product that we are talking about. So you know Seagate, we are the data management company, and our most significant product is the hard drive. One thing is, every day I marvel at what an engineering beauty this hard drive is. Like, if you just look at every aspect of it, it's very complex, sophisticated, and everything precisely designed to work together to help drive the world's information. So there is not a doubt in anyone's mind this should be like this. It is a very, very sophisticated, complex product and requires much, much better care and quality control at every step of the process in making it the product of choice for our customers there. And today we will be talking about that Project Athena, which helps solve or helped improve our anomaly detection and throughput improvement process, specifically with respect to the drive heads within the drive. So if you look at the components within this, if you take within a disk drive, I'm making it very simple to see the parts of interest. Of course, you have the drive assembly. You see it at the bottom. Then you got the spinning disk themselves, and then the drive assembly. In each one of those drive assembly, you have the read-write heads. So our focus is on where the process of manufacturing those heads and how we applied AI and machine learning to improve that process. And why we chose that specific the drive heads? Well, to put this in perspective, someone explained to me in a very simple way, which I really like, and I want to share that explanation with you. Imagine when you look at a drive head and then the drive spinning underneath it at a high speed, it's the equivalent of a large 747 flying not at this normal speed, but equivalent of flying at 800 times the speed of sound and flying just even less than an inch from the ground, and then trying to access every bit of information that is underneath it. That's what a read-write head flying over a disk looks like. So you can see that what level of precision is needed and how everything needs to line up and work perfectly to make this work every time. So if there is any doubt this is an ideal case for applying smart manufacturing use case, it should be gone by now, if I may. So the making of the drive head itself, it's a very complex process, naturally. It takes about 1,400 steps or so over a period of about 5 months. And it starts with the drive head itself. Finally, it measures a few hundred nanometers in diameter, but it starts with wafers, like discs that you see there on the left side picture. They're about millimeters in diameter there. So from there, through this 1,400 steps, we get cuts and slices and stacked into making the drive heads over the period of 5 months. And as I said about the high volume part, we make a whole lot of this drive heads. Like each one of these 200 millimeter wafers disc that you saw, that get cut into about 100,000 or so sliders. And we make about 1 billion or so sliders per year. And we have manufacturing facilities across, I believe it's about several different countries and 7 or so installations where we make this drive heads there. So you can see that it fits the category of high precision, high velocity, as well as the volume of production that fits in here. So what happens if during this wafer manufacturing process, wafer to head assembly process, we find one of those wafers have an anomaly? Well, one thing, at the end of this 1,400 steps, you find out it's a long wasted production cycle having worked with a wafer that's not up to snuff. Or you may not find the problem at all during a normal process, and the problem may manifest only after this is assembled inside the drive, and even the drives may get shipped over to the customer use there. And in general, because of this particular complexity, you have overall loss of efficiency, productivity, and more. And you're constantly having to relook at your quality control process, retain your employees. All those things overall results in suboptimal way of producing, right? So we ask the question, what if we can catch this anomaly sooner? Well, what if we can get this before going through all those 1,400 steps? That's where we started out with. Well, I wanted to, before going into how we solve this one, we just want to show you how complex this question in itself is. First, I want to pose the question, what is an anomaly? So here are some of the pictures that are taken by the electron microscope of during one of those 1,400 steps when the wafer is cut into make the drive heads there. These are all marked at different timestamps and everything. Well, which one of these pictures really makes it an anomaly? It does need an expert knowledge, people who have looked at it before and be able to, during the process, that's where we said about 20, 30 decisions per minute, they need to be able to look at this and very quickly say, that doesn't look right there. And then next the question of, okay, how many such anomalies do exist so that you're all trained to find out every one of them? That means we need to be able to document and codify every possible type of anomaly there. But you know what? The anomalies are not just a fix-it. They constantly change. And when they change, what do? Like, we do use some level of rule-based AI. It's not how a fully human decisions made in there. The rule-based AI system, how they work, is you pre-program them with this known set of anomalies. You tell them, I know of this 200 set of anomalies. If you see any one of them, you make a decision. Well, fine. If your anomalies are all only those 200, or they fit exactly those 200 there. What if even if there is a slight variation? What if it's a combination of those 200? What if it falls between the gaps of those 200 or outside? So those things are not possible to do today with any of our rule-based systems there. Of course, you could ask the extreme question of like, well, if quality is that important, why don't we get a really restrictive system? Like, even if it smells of something is problem, like we'll just reject it, right? It's a really too restrictive process. Well, in that case, what happens? You end up rejecting many good quality products that results in lower yield. Things that would be otherwise good, because we want to be extremely careful, we rejected them. On the other hand, is the too lenient, where you're passing through many of them that may not, that should be caught. You end up accepting flaws and then end up with bad finished products in there. So somewhere in between the two is where we want the Goldilocks range of finding, optimizing the right level of quality control and maximizing the throughput that we want to achieve. And that level of attaining this Goldilocks range is not possible with rule-based or purely human-based, or even combination of rule-based systems plus humans as well. This is where we found the gap, where it needed a new way of solving, and hence we introduced this project Athena, which employed the machine learning and deep learning methods to help solve this. I want to give you before I go there, I want to give you a good side note in here. Someone else asked me this morning the question, so I thought I will share with you the use of the terms artificial intelligence, machine learning, and deep learning. Well, what's the difference really between all those three? Well, first thing is the artificial intelligence existed for a long time, and it works more of a fixed rule-based way. Like, you try to program it with a set of rules, and it tries to act like, okay, if this, then that kind of mechanism. There's nothing self-learning or otherwise complicated. If you want to change something, you need to study the system and you need to manually program those rules into it every time. The machine learning and deep learning it's the equivalent of like how early days as humans we try to learn a task by observing and doing many, many times over. So we try to teach the machine, instead of teaching it the rules, we let it discern its own rules and be able to apply it. Deep learning is nothing but machine learning with more layers, like so it gets a little more sophisticated each time there. So I've seen that used sometimes interchangeably. On the other hand, I've also seen some people insisting don't say machine learning when you mean deep learning, but they all fall in the same category in terms of the level of sophistication that you'd see. The difference really comes down to, with artificial intelligence, you need rules, you need to program the rules. In the machine learning, deep learning, you let the machine figure out what the rules are by giving it many, many samples and training it to see that one. With that said, let's show you how we solve this, achieve that Goldilocks range there. Well, I told you about our production process that captures with the electron microscopes along the way, captures images of those wafers. So we do capture about 17 million or so images per day. And we do have a collection of about hundreds of thousands of them over the period that we have seen and known as anomalies there. And we used one other programmatic way to identify and classify and tag them. There's many different ways of known set of anomalies. So using the combination of these two, we built a neural network model, a deep learning model, that runs on NVIDIA GPUs that are housed in our partner HP servers, where we train the models with these images that we have tagged as anomalies, so that it builds in a very complicated internal model of what constitutes an anomaly and what's not. If you go back to those very sketchy images that I showed of 2 slides back, It's the equivalent of training the machine with over and over and let it figure out what's good and what's not an anomaly. And one good thing about the machines that's different from human is they can also, when they make a prediction, say this is an anomaly or not, they also give the confidence level. They give like, I'm 99% confident or I'm 90% certain this is an anomaly. So that's another added advantage there. So once we built that training model, then we deployed it to help during the production process to help make the prediction. So as the images come off the production line, as the wafers move through those 1,400 steps, the trained model consumes those images and very quickly make that prediction there, well, if it's an anomaly or not. So this happens much faster than just our current mechanism, and it frees up our experts to solve much bigger problems instead of having to stand there and help make this simple decisions here. And because the model is self-learning, it can identify all those gaps, not just those 100,000 that we trained it with. It can identify any combinations of this, any variations of this, any gaps between those 100,000s in there. It knows and helps make that prediction there. That helps significantly improve our overall quality, overall throughput, as well as freeing up our resources to do some of the bigger problems there. In essence, this is a real-life, real production use case of applying deep learning, GPUs, and edge analytics to help solve a factory use case, taking our factories to the smart manufacturing era. And when we started and opened this conversation with edge. Well, where this system is built up, where the training and inference happens, it happens on our factory floor. It's at the edge. We do not have the bandwidth or the waiting time available to send all this data over to a cloud to have that process and come back to help make a decision. So both the training and this inference process happens on the factory floor, that is the edge in this case. To bring it all to a good summary of the high-level benefits that we achieved. Well, we saw a problem, a real problem that needed a solution, but no off-the-shelf solution is available. High precision manufacturing, like high volume of image files that is getting created, and the latencies are so short, we can't afford to send it over to somewhere, get it processed in the cloud and come back. We needed real-time analytics now. So in the absence of anything that is readily available, our data scientists internally working alongside the partners help build this reference architecture, which leverages Seagate's own all-flash array, the NitroX 324, for storing the training data and analytics, and work with the NVIDIA GPUs and some of the TensorFlow and other deep learning models that are available. And also built a future-proof architecture where once you store these images, they're not going to go away. We needed also a longer-term storage. So 4 years from now, if I want to read in the model, I have the images available to have an archival storage as well. So we built a complete 3-tiered model to solve a business problem at the factory. As a result of this, we're going to see the benefits very soon. Some of the predicted benefits are, well, we expect to see the throughput improvements. And also it helps defer some of the investments that are needed in building the clean rooms. And overall improvement across all our current investments. And we predict that with the investment that we made to help solve this problem with our architecture, our models predict we're going to get 300% ROI easily just from this productivity and throughput increases there. So it's this architecture paid for itself 3 times over there. And with that said, like now you would want to know where can you find the exact technical details of it, or find out the very specific problems or how you go solve it. So we have a white paper written with the reference architecture that should be going online in the next very few days or so. So that will be available in labs.seagate.com. So as we complete this webinar and as Joshua sends out those emails to you, you will have the link to where to go and find that white paper as well. But in any case, labs.seagate.com is a great resource with many other topics like this. You should be able to bookmark it and see it as well. And also, if you have any specific questions after this, as you say, or if you want to take this architecture and go apply in a similar scenario, or your customers are asking about it, drop us a note at livelabs@seagate.com. We'll be very happy to answer your question, have our data scientist team help you meet with your customers and help make this one happen as well. And lastly, before I open up to Q&A, I do want you to direct to another report that came out from us today. It's called the Data at the Edge. So I encourage you to check out www.stateoftheedge.com. We published an ebook that talks about the amount of data that is getting created at the edge and what should be different about storing, managing, and orchestrating this data at the edge. So you should be able to download this report free from stateoftheedge.com. With that said, this is now time for Q&A as Joshua comes in to take the questions.
Yeah, you bet. Let me quickly pivot here. Okay, we're back. All right, let's take a look at some of the questions here. But we want to make sure that we haven't covered them already. One of the questions that came in, Rags, you talked a little bit about AI versus machine learning versus deep learning. We have folks that are wanting to know, can this same solution that we've talked to work in other factories, maybe other verticals? Kind of a general question, but thought you could address that as we kick things off.
Yeah, absolutely. So when we set out to solve this, we started with the problem first. We didn't have a solution. We saw look, there's this process is complex. Things are getting very sophisticated. We can't just do the things we used to do the same way. So we set out to solve this. And if we boil down the problem it comes down to finding an anomaly, which is something that doesn't look like the other, that we need to find out and weed out, and do so in a faster way without having to anticipate everything that's coming. So while we solve this for our own factory and for our use case, the solution is anomaly detection. You can take this and apply in other scenarios, say, for example, video analytics in a surveillance or in an autonomous vehicle, where everywhere you have a similar anomaly detection needs. And finding out which one of them doesn't look like the other that you need to make a specific decision on. Yes, the solutions in the architecture you see when you download the paper, you should be able to, with a few tweaks, with the better training data, should be able to apply that to any of those use cases that needs an anomaly detection.
Great. Had an interesting question. Paulo sent in here about, do you see the computational power moving into the storage element?
Yeah, so one thing we are seeing more is the move away from more of the hyper-converged to more of disaggregated or sometimes used as the composable. So we do storage management really well. And we see that some of the compute elements, like the GPUs, I think, they do the computation extremely well. So we need the best of those two worlds to work together, see that as the right solution. So more of the integration value comes from the SIs and solution partners who help them make together, rather than trying to push more of one aspect of the, say, more compute into storage, or trying to add even more storage into that server boxes there. So we see storage getting better in terms of performance, help solve the problem, working in conjunction with the compute box, be it the GPU-driven or other, to help solve the computational problem. So it's more of a disaggregated architecture is the way.
Yeah, only the future will tell, right? We do have folks who attend these webinars that are end users or interested parties, people who are, decision makers. We also have resellers, and we actually have one who reached out who wanted to know kind of what are the near-term opportunities for resellers in this sector, right? There's a lot of different directions you could go with that.
Yeah, definitely. So when you talk to your customers, we say we started out with data as potential, right? Like everyone across the board, every industry is now asking the question, how can I put data to work in my business? How can I improve my throughput? How can I improve my employees' productivity? How can I improve some of my quality process in there? They're all intrigued and looking at how to put the data to work with many of the tools of artificial intelligence and with some of the computational advances like GPU. So you want to ask and pose the question of what is their future look like in terms of manufacturing process or just process efficiency or throughput, or even if it is a retail, like overall output increase and throughput increase in those cases. So to bring them back to the conversation of like, what is their strategy to capture, store, and activate the data to capture the business value in it. When some of them who have thought through this may be able to share with you, or in these cases where they are not, that may be the person like, have you looked at a use case like this where we use image-based analytics to help solve a real-life problem in manufacturing? That could be of use in your situation as well. To be able to open the conversation with them, if they are thinking about it, you asking the question will put you at a very high level of engagement with them to open up for, be it the storage sales or more of a solution engagement. Or if they are not thinking about it, you become their trusted partner, engaging and educating them of some of the possibilities. And if you think a conversation that we can help with from our architects and others, or with our white papers, we'll be happy to help you and do a deeper dive when it is needed. Yeah,
and I think just the very fact that we're doing this session, right, is a great example of, we're practicing what we preach, right, and sharing out those key learnings, kind of boldly forging ahead. We did have one question that came in, Rag. Somebody, this is the cynic in the group wants to know, after listening to this, does all this just eliminate human operators?
So I did put a kind of a slide in the beginning there. No, it's not the case there. It changes what we are going to be doing. So our human operators are very smart, high-order people, but we've been using them just to make those quick decisions there, right? So now when we have this kind of decision-making move to a programmatic method, it frees up their brain cycles to do some of the more complex problems. Now, how do we make the next quantum jump in both in productivity and quality? They help solve the bigger problems in there. It only frees up all these things. They don't eliminate us. They only help frees us up to solve some of the bigger problems we're going to be doing there.
Yeah. We did have someone that jumped in and wanted to know what the general consumer market benefit is, from this new sector, right? We talked about, increasing yields, and I mean, there's a lot of different ways you can see this going, right? Yeah,
definitely. Any one of them. Like we were recently, we had a gathering of professionals at the NVIDIA GTC conference where we had an happy hour and talked to several practitioners like this. There were people from outside consumer products, packaged good products groups, and they were talking about the similar problems. They also want to apply data and machine learning to help improve their productivity, and they were asking about how much data to collect, how do I store the data, and how do I keep the data over a longer time, or asking about those key questions there. So across the board, but data drives everything at this point. So any industry vertical you will see used for data storage and applications like this.
Got it. Yeah, I think a lot of this is just to me it's a great thought leadership play, and like I said, Seagate Insider is a great program. We'll be sharing this out with anybody who sees a need, wants to join. Like I said, we do have a monthly newsletter that we do highlight articles like this, sessions like this. So definitely make sure you come by the site, and there it is for you, seagate.com/partners is a great place to get hooked in and be on these edge discussions, so to speak. I do want to highlight here that we do have a lot of these reports that are available publicly right on our site. So Rags talked about the initial report. You'll see here the case study, but do pop on by for the reference architecture, the white paper. The labs.seagate.com is a great reference. So here again, we're doing what we can to make sure that we're offering a little bit of voice of reason for what's coming down the pike. As we wrap things up here, Rags, any final words you'd like to share?
No, this has been a great conversation sharing with you. Again, different from the other presentation, it's not about selling a particular product to you, but more of exposing you to some of the cooler technologies that is happening and also making it real. It's not an edge, and AI and machine learning are not just some distant concepts. They are real, and they are here, and we are living it, and we are happy to share our knowledge and experience with you.
Great. Couldn't have said it better myself. Well, many thanks everyone for attending today's session. Check out the Seagate website, and related to this session, head over to the Enterprise Data Center tab and click on the IT 4.0 link. There you'll find full research paper we highlighted today, as well as more info on this emerging topic. My name is Joshua Walty. Thanks for attending. We look forward to seeing you guys all in a future session. Thanks, everybody. Bye-bye.